Welcome to Chapter 10, Part 1. This video covers 10.1, 10.2, and 10.3, where we'll be looking at area of different shapes. So all of the shapes that we've covered in the last few chapters, including our quadrilaterals, our special quadrilaterals, and in Section 3, general polygons. So our objective for Section 1 is to find the area of parallelograms and triangles. Those are kind of our base shapes, and all of these areas are based off of these parallelograms and triangle areas. So this is a very important section to understand. Hopefully, some of it is familiar. In order to find the area of a rectangle, we know that we can multiply two of its perpendicular sides, base and height. Sometimes they're called length and width. And we can actually use that same formula for a parallelogram, because if I kind of cut off this triangle over here and put it on this side, we end up with a rectangle. And so the area of a parallelogram is exactly the same as the area of the rectangle that it would make. So just like with a rectangle, we have a base and a height. We're going to define those here for a parallelogram. The base can be any of its sides. I could pick any of the four sides of a parallelogram to be the base. The altitude will be the segment that connects that base to one of the vertexes that is not on that base, and it has to be perpendicular. So the base is perpendicular to the altitude, and the height is the measure of the altitude. So let's try some examples. I'm going to go ahead and let you give these ones a try, and then we'll go through them together. So for part A, we need, this is a rectangle, area is base times height. Doesn't matter which one we call base or height. 6 times 8 is 48. For part B, we have a parallelogram here, so we want a side and the altitude that's perpendicular to it. If we choose the 4.5-inch side, we don't have the measurement of the altitude perpendicular. So we want this to be our base and this to be our height, because we're given the measurements that we need to find base times height. So 5 times 4 is 20, and I should be putting units here, squared inches. For part C, again, we want to pick the two lengths that are perpendicular to each other. So the base here, just the length on the parallelogram, just two. Not the length from the corner all the way to where the perpendicular line is drawn, but just the part of the parallelogram. Base times height, 2 times 3.5, this is base, this is our height, is 7 squared centimeters. And finally, part D, even though this is a square, same as a rectangle, area is base times height. 7 times 7 is 49 square miles. For a triangle, we're going to use a very similar formula, except it's been cut in half. So think about if I take a triangle and I rotate it 180 degrees, it would give me another triangle right here, making a rectangle. So the area of a triangle is half of the area of a rectangle. That's where this 1/2 comes from. Just like a parallelogram, the base of a triangle can be any of its side. The corresponding height is the length of the altitude to the line containing the base. Okay, so again, altitude means that it's perpendicular to the base. The height has to be perpendicular to the base. Let's look at a couple of examples here. Again, I'm going to give you a chance to look through them, and then we'll do them together. Part A, all I have the three sides of the triangle. The base and height need to be perpendicular to each other. So I want to see if either of these are perpendicular, any of the sides are perpendicular to each other. So here we have area equals 1/2 base times height. These will be my base and height because they are perpendicular to each other. So area equals 1/2 4.5 times 6. We can put that straight into the calculator and we get 13.5 square yards. On part B, again, we're looking for a base and height that are perpendicular to each other, but just the measurements on the triangle. So 2 feet of the triangle, this 2 feet is extra information. We're not going to use it. The perpendicular height is 3 feet. Area equals 1/2 base times height. 1/2 times 2 times 3 equals 3 square feet. Let's take a look at section 2. For section 2, we're taking our areas of parallelograms and triangles, and we're going to use those in order to find the area of trapezoids, rhombuses, and kites. So to find the area of a trapezoid, we're going to use the area of 1/2 height times the sum of the bases. So again, this is very similar to a triangle, 1/2 base times height, but the base is actually made up of both bases of the trapezoid. Okay, so the height of the trapezoid is the perpendicular distance between the bases, just like the height for our parallelograms and our triangles. If we look at this diagram in the next example, and we assume that it's a trapezoid, what is the approximate area of Nevada? Now, Nevada is not a perfect trapezoid, but it is pretty close. So in order to calculate this, we need to first find our bases, and those are the ones that are parallel to each other. So we have those 2 bases, and then we have to find the perpendicular distance between them. This will be our height. So area equals 1/2 base times height, but we have 2 bases, and we're going to add them together. This is 1/2 base 1 plus base 2, that's 205 plus 511. And again, addition, it doesn't matter which one you put first. And then the height is 309. Put that into the calculator. We get 110,622 square miles. Okay. Now, why is this distance in miles and this is in square miles? Well, an area is covering 2 dimensions. So remember way back when we were defining our point line plane, we talked about dimensions. A line is only in 1 dimension, so the exponent here is miles to the first power. 1 dimension, so we don't put the exponent. Area is like a plane, it covers 2 dimensions. It goes this way and this way. And therefore it is miles squared, 2-dimensional area. For a rhombus or a kite, we have a very similar formula, except instead of multiplying base times height, we're going to multiply by the diagonals. And the reason we can do this is because just like base and height being perpendicular, for a rhombus and a kite, the diagonals are already perpendicular. And that means we can use this formula for a square as well. So we have area equals 1/2 times the length of the first diagonal times the length of the second diagonal. So let's look at our examples. What is the area of the kite? Well, area equals 1/2, not base and height here. Now it's diagonal 1 times diagonal 2. So we need to find the lengths of our diagonals. Well, our first diagonal, LN, is 3 and 3 more. 3 plus 3 equals 6. I've seen some people trying to multiply these 2 values, but if I multiply 3 times 3, that would be a square, a 3 by 3 square, right? That would be an area. So we're not multiplying these, we're adding them, because if I have 3 inches plus another 3 inches, that gives me 6 inches, not 9 inches. So be careful with that. Our other diagonal is KM, and that has 2 and 5 more. 2 plus 5 is 7. So we'll call that diagonal 1 and diagonal 2. 1/2 times 6 times 7 is 21. Again, this is area, so it's square meters. And part B, the area of a rhombus. Again, we are looking at the diagonals. However, in this case, we aren't given the length of both diagonals. So we have to do a little bit of calculation here. So a rhombus, we know, has bisecting diagonals and that they're perpendicular. But we have, instead of the second diagonal, we have the outside leg. So how do we find the length of this inner leg? So this is 8 and 8. We need x. Well, because we know these are perpendicular, we can use Pythagorean theorem. If you recognize this as being a Pythagorean triple, you can also use that instead. So we have x squared plus 8 squared equals 10 squared minus 8 squared. X squared equals 100 minus 64, which is 36. X equals the square root of 36, plus or minus, but we always choose the positive for distance, equals 6. 6 and 6. So diagonal 1 is 6 plus 6, which is 12. Diagonal 2 is 8 plus 8, which is 16. If you called this one diagonal 2 and this one diagonal 1, you will still get the same answer. It doesn't matter which one we call first and second. The area equals 1/2 diagonal 1 times diagonal 2. That's 1/2 times 12 times 16 into the calculator is 96. Units are inches, second dimension, so it's inches squared. Let's look at a couple more examples. So the first part of finding the area of these shapes is to identify what shape it is and which equation we will use. So looking at this is a trapezoid. For a trapezoid, we have 2 bases and the height. Area equals 1/2 base 1 plus base 2, so that's the bases, times height. 1/2 bases times height. This is a triangle. For a triangle, we use area equals 1/2 base times height. For number 3, this is a kite. For a kite, we use area equals 1/2 diagonal 1 times diagonal 2. And this is, well, we don't know for sure if it's a rhombus, but we do know that it's a parallelogram. So we'll use parallelogram, which is area equals base times height. Go ahead and give these ones a try, and then we'll work through them together. So for number 1, area equals 1/2 base 1, which is 6, plus base 2 is 3, times the height, which is 5. So then the area equals 45 halves, or 22.5 square miles. For number 2, area equals 1/2. Base and height have to be perpendicular to each other. So we're going to call this is our base and this is our height. So then that's 10 times 4, which is 20 square yards. Here we need our diagonals. Well, here I have 12 and 8, giving me 20 for that diagonal. But for the other pair of diagonals, I don't have the length. So we have to, again, use the Pythagorean theorem. Here is our hypotenuse. 13 squared equals 12 squared plus unknown squared. This is a Pythagorean triple, so if you recognize those, you don't have to use Pythagorean theorem. Minus 12 squared. X squared equals 169 minus 144. X squared equals 25. X equals the square root of 25. plus or minus, but always choosing positive for distance, equals 5. Because this is a kite, we know that these parts of the diagonal are congruent. 5 and 5 gives us 10. So area equals 1/2 times 20 times 10, which is 100. We don't have units, so we won't put units. And number 4, area equals base times height. Well, this is perpendicular, but that also means this is perpendicular because of alternate interior angles. It doesn't matter which one we choose as the base, they have the same value. But this is definitely our height. So area equals 5.4 times 4 equals 21.6. This is centimeters squared. Let's take a look at section 3. In section 3, we're looking at the area of regular polygons, and this leans very heavily on the area of triangles specifically. So to find the area of a regular polygon, we first have to recall some vocabulary. A regular polygon is a polygon with all sides and angles congruent. Okay, we're also going to use some new vocabulary where the center of any regular polygon is the point exactly in the middle. Think about when we were doing our construction, we started with the center of a circle and then we created the polygon around that center. The radius of a polygon is the distance from the center all the way out to the circle, which is at the vertex. So from the center to a vertex is the radius. It's important to distinguish that from the distance that's from the center to the side, which is not a vertex because it doesn't, or is not a radius, because it doesn't touch a vertex. It doesn't touch the circle. Instead, that length that doesn't touch the circle, it touches the edge of the polygon, is called an apothem. So here we have the center of the circle. We have all the way out to the circle is the radius, and out to the polygon, but not all the way to the circle, is the apothem. If we have a regular polygon, all of the radii will be the same value. And that means that these triangles will all be isosceles triangles. So how do we find all of the information that we need in order to calculate the area? Well, we're going to need to calculate some angle measurements. So first, if we have our polygon split up into these isosceles triangles, we want to know what this angle in the middle is called. And that angle, angle 1, is called the central angle. It goes to the center, it's the central angle. Okay, so in order to calculate this central angle, we're going to take 360, which would be if we could take the whole circle, and then we're dividing it into all of these pieces. So I took a circle, divided it into 5 pieces, and that's how we'll find the central angle for a pentagon. All regular polygons will have, so for example, all regular pentagons will have the same central angles. All regular hexagons will have the same central angles. Okay, so in this case, because this is a pentagon, n equals 5, so the measure of angle 1 equals 360 divided by 5, which is 72 degrees. Because these are isosceles triangles, the apothem, which goes all the way down to the side of our regular pentagon, actually creates a point at the middle. So that's actually a midpoint of our base, and it therefore also bisects this angle. So the apothem bisects the central angle of a regular polygon. So in order to find the measure of angle 2, which is this one that I've kind of drawn all over, angle 2 is the central angle between the apothem and the side here. So half of the central angle. So we would take 72 divided by 2 to get 36 degrees is the measure of angle 2. And since we know the sum of the angles in the triangle is 180 degrees, and we have this triangle here created by the apothem, the radius, and half of a side, we know that this angle here was 36 degrees. And so the measure of angle 3 is 180 minus 90 minus 36. Anytime there's a 90-degree angle, we can also think of it as 90 minus the given angle, which is 54 degrees. So that will be the measure of angle 3. So again, pulling in information that we've been building up throughout the past few weeks. So let's start by finding just angles. We're not going to jump right into area. First, we'll just find some angles. All of the numbered angles. So we need the measure of angle 4, the measure of angle 5, and the measure of angle 6. Well, first off, this is a square. One thing that we know about squares is that their diagonals bisect each other at right angles. They are perpendicular bisectors. And therefore, the measure of angle 4 must be 90 degrees. With our new method, we can also say that this is 360 divided by 4. Notice you'll get the same answer. The measure of angle 5 is half of that. So 1/2 of 90 degrees is 45 degrees. And the measure of angle 6 is going to be 180 minus the measure of angle 5 minus 90. But as we were saying above, anytime you have a right angle in your triangle, the other two must add to 90. So I'm going to skip that step. We're going to use the shortcut. 180 minus 90 will always give us 90. So we can say this is congruent to angle 5. 90 minus 45 equals 45 degrees. Okay. For number 2, we're doing the same thing, except with a hexagon. Go ahead and try it. So here our number of sides is 6. To find the measure of angle 7, we do 360 divided by 6, giving us 60 degrees. To find the measure of angle 8, we take 60 degrees divided by 2, or times 1/2, to get 30 degrees. And to find the measure of angle 9, since this is angle 8 and this is a right triangle, we can do 90 minus angle 8, which is 60 degrees. So these are our special triangles. This is our isosceles right triangle, also known as the 45, 45, 90 triangle. And this is our 30, 60, 90, or our half equilateral triangle. That tells me that each of these triangles made from the central angles is an equilateral triangle. Let's take a look at our next page. So now we're getting into how do we actually calculate the area. And those angles are going to come into play because they're going to help us find the side lengths that we need in order to calculate the area. So the area of a regular polygon is 1/2 times the apothem times the perimeter. Where does this come from? Well, if I were to draw in all of my radii, notice these make triangles. So I have base and base and base and base and base and base. And if I add up all of those bases, I would get the perimeter. Perimeter equals all of the bases added up. Okay, so this is a shortcut for 1/2 base times height, where base is added up give us the perimeter, and A, the apothem, is the height. So A is the height, and bases are the perimeter. Okay, so it's really the area of a triangle, but then we're adding them all up to get the polygon. So let's find the area of this regular decagon. Decagon tells me 10 sides. Regular means they're all the same. So if I have one side is 8 inches long, then the perimeter equals 10 sides, each of them is 8 inches long. This is 80-inch perimeter. The apothem is 12.3 inches. I can tell that because it is perpendicular to my base. Area equals 1/2. Instead of base, we have perimeter. Instead of height, we have apothem. 1/2 times 80 times 12.3 into the calculator is 492. Units here are square inches. Okay, let's take a look at an application of this. Honeycombs are made out of regular hexagonal cells. The length of a side of a cell is 8 millimeters. What is the area of the cell? Okay, well, what do we know? We know that we have a hexagon. Let me say regular hexagon, where each side is 8 millimeters. So let's draw it. Here's my hexagon, 8 millimeters, and they're all the same. Okay, what have we previously learned that can help us? Well, we know that a hexagon creates 6 triangles, and specifically what we've been seeing and observing is that it makes 6 equilateral triangles. I shouldn't put another tally mark. 6 equilateral triangles. Hexagons create 6 equilateral triangles with the central angles. Why is that helpful? Well, if we know that this is 8, this is 8, this is 8, all of these are 8 millimeters, then we can find the apothem. And how do we find the apothem? Well, how do I find the height if I know that this side is 8? So I'm going to draw this out again. Here's my apothem. This side is 8. I just cut this side in half, so that's 4 and 4. And I need this other side. Well, remember our 30, 60, 90 special triangles? This must be 4 square root 3. You can also use Pythagorean theorem. So what can we find? Apothem by special 30, 60, 90 triangles. And then we want to find what is the area of the cell. Area equals 1/2 AP, 1/2 times 4 times the square root of 3 times my perimeter. Well, I have perimeter is 8 millimeters times 6 sides, which is 48. 1/2 times 4 root 3 times 48 is 96 times the square root of 3 millimeters squared because it's an area. Let's look at our next example. We want to find the area of each regular polygon. Well, here we have a triangle. Splitting it into its central angles, we know that each radius is 4 inches long. So how can we use that to help us? Well, if I draw in my apothem here, this has created a triangle, a right triangle, where the hypotenuse is 4. Because this is a regular polygon, I know that this is an equilateral triangle where the angle measure is 60 degrees, which means that the radius cuts that in half, 30 degrees, 30 degrees, 30 degrees, then this must be 60 degrees. So this is a 30, 60, 90 triangle. Drawing in the other half of my equilateral triangle, this must be 2, so this must be 2 root 3, and that is the base, well, half of the base, right? And this is the apothem. I should say base over 2. Because if I'm calling the base the whole side of our triangle, this right here is only half of the base, that would be the full base. So area equals 1/2 AP equals 1/2. Apothem is 2. To find the perimeter, I have 3 sides of the triangle. Each base is 2 root 3 times 2. So the perimeter is 3 times 4 root 3, which is 12 square root of 3. 12 times the square root of 3. 1/2 times 2 is 1, so our area is 12 times the square root of 3 square inches, with only the radius given. For a square, we do the same thing, only the radius is given, so we'll create our central angles. That gives us a right triangle here. We know that the diagonals of a square are perpendicular, so this must create a 45, 45, 90 isosceles right triangle. Draw it down here a little bit bigger. This is 6 centimeters, so then this must be S root 2. This is S. So S equals 6 divided by the square root of 2. Rationalize that. 6 root 2 over 2 equals 3 root 2. 3 root 2, 3 root 2. So my apothem, the one inside of my polygon, is 3 root 2. My base is 3 root 2 plus 3 root 2. Notice every time I'm creating this little triangle made by the central angle and the apothem, it's only giving me half of the base. So the base is 6 root 2. The perimeter, there are 4 sides. Each side is 6 root 2, giving us 24 root 2 as the perimeter. The area equals 1/2 AP. 1/2, apothem is 3 root 2. Perimeter is 24 root 2. You can put this into your calculator or you can calculate it by hand. Square root of 2 times the square root of 2 will give you 2, times 1/2 is 1. So really what we're calculating is 3 times 24, 72. Our units here are squared centimeters. Let's take a look at our last page. Continuing from the previous example, we're finding the area of a regular polygon. So this is a regular hexagon. Again, I'm going to draw in the central angle and the apothem. Draw my triangle bigger. If this whole side was 22 feet, the side of the little triangle that I just drew is 11 feet. This is a hexagon. Hexagon says this central angle is 60 degrees. So this angle here is 30 degrees, leaving this other angle as 60 degrees, again giving us one of our special triangles. If this is 11, then this must be 22, and this is 11 root 3. Area equals 1/2 AP. My apothem, this one here, is 11 root 3. Perimeter, there are 6 sides. Each side it was given to us is 22, giving us 132 feet. So this is 1/2 times 11 root 3 times 132 into the calculator is 726 square feet. Oh, square root of 3, sorry. 726 times the square root of 3 square feet. For number 4, we're finding the area of a hexagon with a perimeter of 72 centimeters. It already gave us the perimeter. So start by drawing a picture. Always, always, always draw a picture. I create my central angle sliced in half by the apothem. Here's my apothem. So the perimeter is 72. Well, the perimeter is broken up into 6 pieces, so each side is 72 over 6, which is 12. That makes the whole side here 12. So then my small triangle, if the whole thing is 12, then this side is half of that, which is 6. Again, we get our 30-60 triangle by saying this whole angle here is 60. Each of these central angles is 60 degrees. And so the angle, when I cut it in half by the apothem, is 30. 30, 60, 90 triangle. If I draw in the other half of my equilateral triangle, I see that the 6, 12, 6 root 3. So the apothem is 6 root 3. Area equals 1/2 AP, 1/2 6 root 3 times 72 equals 216 root 3, and units are centimeters, squared centimeters. Okay, we'll be practicing more in class, but it is very important that you have that solid understanding from our previous sections about the special triangles, about the difference between your different polygons, and how to find those angles.